Hi there, my name is Christopher Wurst and welcome to the 5th video in the second playlist for Homework 2 for material energy balances. This homework's going over question 5 that says on your screen, using the Maxwell construction, plot the two-phase envelope superimposed on the PV isotherms of part 3. That's a lot. So we have our isotherms here. So what we want to do is remember from the PV isotherm graph, this bump here where the liquid and gas phases mix, and thus the temperatures can't physically be taken well, this connecting line here is there. This line here is what we want to put on. So we're going to be using the Maxwell construction. Now the Maxwell construction is part of the van der Waals equation, or it's used with the van der Waals equation, where if you look at this line here, this dip and this rise, there is a pressure called equal pressure, where the area underneath the pressure, this line, in this dip, and the area above come out to be 0, so they're equal. So we're going to be using the Maxwell construction, using some integrals and some Python code to find the specific pressure and then plot that on the graph. So to do that, I'm going to start by importing one more thing. I'm going to be importing from SciPy, Scientific Python, SciPy, integrate, import quad. This takes integrals. It's much easier to do than, say, if I were to do Wolfram alpha. I'd have to type in the entire integral, and that's a pain. I'll mix up the parentheses, I'll screw up typing it in, it'll be wrong, I'll freak out about it. We're just going to use the quad equation to do it for us. So, to start, we're going to make a function to do that. So we're going to be defining cubic quad or quadrature with the terms P and T, pressure and temperature, as our inputs. Now, we want another function here for our integrand, what we want to integrate over, and there we are going to input temperature, actually not temperature, sorry, volume. And we're going to return, we're just going to return one thing, return pressure minus cubic pressure with volume and temperature. So this will be the pressure, the gas minus the cubic pressure up here, which gives us the pressure from the van der Waals equation, which is, of course, error between guess and the value that returns. So we're going to take we're going to also use cubic V, or cubic volume, the function that we did last question, and we're going to put V1, V2, and V3 is equal to cubic V for, we want pressure and temperature, so P and T. And then we're going to return, we're using quad for the integrand, the difference between the pressure that our gas is and the cubic pressure with said volume and temperature. Integrand given V1 and V2. And we also want a first value from it. And we're also spelling error. Integrand, here we go. And we're doing the same thing for the integrand from volume 2 to volume 3. Now, what this will do is it will give the areas from here, this area here from volume 1 to volume 2 under this curve, and the area under here from volume 1 to volume 2 here. So, Shift Enter. Cool. So integrand, again, the difference between the cubic pressure and the pressure guess. Volume 1 and volume 2, the first two of the cubic volumes. We also need the first value here, and then volume 3 there. All right, Shift Enter. Now, we're going to check that this works. So we're going to use cubic quadrature, say 91,000. We want this to be as close to 0 as possible, which means that our areas are as close to each other as possible. Say 313.15. Shift Enter. Cubic quad, name quad is up. Cubic it's not refined. Oh, did I did. Shift Enter. I forgot to put actually make quad a thing in this this. Probably divergent or slowly convergent. That could just mean that our value is off. Probably divergent or slowly convergent. Still. Actually, as it turned out, here. So, obviously, I accidentally got that wrong. However, I did in fact catch it now. So, the values that we came up with earlier were wrong, but here, we're good. Yeah, I mean, you can see the difference here versus plus. That's better. And let's try that again. Shift Enter. That's much better. Okay, now that these actually converge, we're good to go. We're good to move on. So I'm also going to change this name to not cubic. We're looking for the areas. So areas. Shift Enter. It should be areas as well. There. We want to define a function that figures out that assigns the values left and right, the left side obviously being the area here, the right side being here, and returns them added together in order so we can take the root of it and drive it as close to 0 as we can. So define, let's call it area diff with inputs same as areas quad, p and t, and we'll call it areas. Better. Now, all we need to do is say left, right is equal to areas quad p and t, and we can return the left plus right. So what that does, Shift Enter, good. So what that does is simply assigns values to these values here, or these values here, and then adds them together to get a value, a returned out value that we will then root, use the root function to drive as close as 0 by changing the pressure. So next we're going to want to do that for a bunch of different temperatures. Again, like we did with these, with the cubic pressure here, and in order to create this this graph, we want to do the same thing except for one line that is going to be a specifically correct line. So let's call it P or P VAP or P VAP. PVAP list. There we go. Equals there. It is now a list. We have an array. We can add it we can add to it. Now, we also need two other things because remember, if we go back, we had the vapor here, which was it was an array. We used an array here and an array here, or well, we repeated it for t in range, but this would have been an array if there was a way to make it an array. So we need to make volume arrays. However, if you remember, using isotherms, to the left here is liquid. To the right here is gas. This area in here is a mix. So we need, not that, here. Again, this area over here is a liquid, this area over here is a gas. We need two different lists for these. So VL list, so liquid volume list, and empty array, and then VG list. And I'll make the, not capitalized, equals empty array. Enter. Now we can take a bunch of different temperatures and create lists and create plot values for them. Now, last time we did, where is it? Here, for T in range, we're going to be using a range again. However, if you look at the constructions or the isotherms, as you get to the critical point, the changes don't get very large. The changes in temperature, or the pressure specifically, stay about the same as you get closer and closer to the critical point. That means that we're going to want to make sure that our guesses, or our changes in temperature, get smaller and smaller as we get to the critical point, so we can continue connecting, so we can continue driving to the middle for our envelopes. So we're going to say for arbitrary variable, say x. X in range, what range should we have? Or not range, NP in space. We want these linearly spaced. NP to lin space, let's start with 0 to 7, let's do 500. Better. Now we can use this to find T. Now if you look at this looks suspiciously like a very, very steep exponential graph. So let's call it an exponential graph. Images. So an exponential graph curves up at an exponential rate, as you can see. Now, what happens if I put a negative exponential graph? Here, it curves down. You flipped it. You can also flip it, but I mean, if you look at that, yes, here, I want to flip it around the top, not the top, the Y, and then there. What we want is, this looks like a exponential graph if the exponential graph was flipped around the y-axis as well. Negative, inverse, negative. Here. So something like this, not the logs. Yeah. So it looks like a logarithmic and or exponential function here. So what do we want? What do we want to do? Well, we want temperature is equal to, say, P dot critical, or critical temperature, minus 275, because that's what our starting temperature is here. So this bottom variable is 275. We want that at effectively 0 times, times 1 minus, so this 1, adding 1 to the np dot exp exponential of t. So this 1 minus shifts it up 1 plus 275. Or not t, negative x. Yes, so negative x makes it flip around the y-axis. Negative exponent flips around the x-axis, so you will get that curve, well, to you it's curve up and around that we want. So, I'll space these out. Better. So now we have that. We also want to print temperature, just so we know that it's working. Now, we want to have vapor pressure equal to the root of, well, we want to root our areas diff, so areas diff. And we need a general guess, because we need a guess for this temperature, for this pressure here. So we'll call it guess is equal to 100, to start at the very least. I also want to make this floats, just in case. So now we have guess, because root expects an array. We also have another argument, so args is going to be equal to temperature. Good. So now we have the root problem here, and we have PVAP, our vapor pressure. So that takes care of PVAP list, and we can add that to PVAP list. But we also need the VL, the liquid volume, and the VG, gaseous volume. So if you go back, V1, V2, V3, well, that's Q's in cubic, the cubic volume, volume 1, volume 2, volume 3. If you look at that, everything to the left of this here is liquid. Here is everything to the left, everything to the left of this, or to the left specifically of this intersection here is liquid. Everything to the right is gas, so you can treat it as such. So we're going to have VL. We're going to be getting our 3 volumes here from cubic V. VL, we need to unpack the second, so we'll call it underscore. It's going to be a dummy variable. We're not going to be using it. And VG, gas volume, is equal to cubic V with, what is cubic V's? Let's look up pressure and temperature. So we're looking for PVAP as our pressure and T as our temperature. Now we can add, so PVAP list dot append is equal to PVAP VL list is dot append is equal to VL, and same thing with VG, the variable. List dot append equals VG. Now, we also want to update our guess to update PVAP at the very least. So we're going to have guess is equal to PVAP. There. Now we can have that. Thank you very much. Now we have entries into our arrays here for and which will repeat every time this loop repeats, and our guess will continue to get updated. Our roots will continue to have to be iterated with the different guess. And the PVAP will continue updating the guess. So we can move on from that. Now, as always with whenever you're updating or adding something to a graph or a plot, you need values for that. You need values for that for the axes. So we need PVAP, call it PVAP list 2 is equal to, what is it going to be equal to? Well, we need PVAP, we need both PVAP list coming forward as well as backwards. So PVAP list as going from beginning to end plus PVAP list from beginning to end, oops, and that needs a comma, beginning to end, and we also want -1, so it will change, so it'll be the reverse, so it goes from low pressure to high pressure, back from high pressure down to low pressure, effectively. And we also want the same for the volume list. So just going to be V list is equal to, let's call it vol vol list is equal to VL list from beginning to end plus VG list, because VG list is the back half of it, from beginning to end, again, the backwards. So, we have that. Shift enter. That's invalid syntax. Oh. Right. Nope. Append. Nope. Here, pvap. Okay. Okay, at the very least, we know that that's good. So, VL as well as VG. Shift enter. Unsupported operand here. Where? Here? Interesting. Well, what does this mean? Look at this. Oh, I wonder. Let's try this. Cubic V. Oh, it could be the temperatures are off. Beta equals beta times P. What is wrong with my cubic V? What is P? Where is P? PVAP. What is PVAP? PVAP is a... PVAP is a value. Why is this wrong? Potentially, we need first the value from this. So we have... Why is this giving me issues? We need the value from the root as well as the first value in that array. Maximum number of subdivisions is achieved, yields no improvement. You can stop now. So there seems to be no issues here, although this here seems to be having issues. Let's just get rid of this. Oh, right, yep, no commas here. List. What is going on? Stop now. Keyboard interrupt. Ask the errors. Why are you having issues? What are you telling me? Yeah, I know. Okay. Equal to cubic V. It's giving me an error. So let's try again. That and T. Try that again. Still doing it slowly. Why are you still doing it slowly? Thank you. I would like for you to stop, please. Evap, root. You know what? Factory reset runtime. We're going to run this from the beginning. Because it seems to have saved some variables from other things. Good, our graph is correct. Cubic V is still correct. Areas. You are still running slow. Why are you running slow? It might be sped up if I just call this a vector and p is equal to vec0. Might be work better. Yes, aha! So it was just slow because I didn't separate out. That's much easier. Well, that's good. Awesome. So we have that there. Now we can simply add our values. So for, let's do fig dot add scatter x is equal to, and I don't want this as pvap list, I would rather call it pvap plot. That's a good conventional name. So pvap plot. So x, shift enter. Once this runs through, I have to exit this out again. Much better. Okay. X is equal to pvap plot. Y is equal to, no, it's actually volume. Vol plot. Y is equal to, please stop clicking, computer. Pvap plot. Mode is equal to lines. Okay. Try shift enter. We have a red one, and I don't want red. Color is equal to white looks better on this. Shift enter. What is the correct marker? Line? What is... Try line color. Shift enter. Yes, that's much better. Would you look at that? That looks much closer to what it should look like. And I want to update the axes a little bit. Fig dot update x-axes. Let's not go to 5, let's go to, or this is 0.01, let's go to 0.01. So what is our x-axis here? This is 1, 10e -7 to 10e -1. Enter. Oh, range, damn. Range equals. Crud. No. How do I get rid of you? No. Well, just get rid of this. Let's redo that. So fig.add scatter x is equal to vol the plotted volumes values. Y is equal to the vapor pressure values. So plot mode to line, then line color is equal to white. Is it mode? No, it's not mode. What is it? Mode lines. It is still, it's still like that. Oh no. Right, it's x-axis is in logarithmic scale, so I forgot that. Fig dot add update x-axis. Let's call it -6 or range equals -6 -1 -1. Call it there. Shift enter. That looks much better, although this needs to be -5, I think. 5. Uh-oh. Oh, that didn't work. Great. So, why, thank you, mouse, for deleting things. Oh well. pvab plot mode equals lines, line color equals white, end parentheses, enter, fig dot update x-axis range equals delete. Here, delete -4 to -1. Shift enter. We'll keep it at -5. Shift enter. There. So at some value here, oh, wrong way. Point. That looks better. So now we can more clearly see this envelope here. It shows where this is. So the value that intersects directly with the top, which is in fact, the blue line's a little bit over the top, which means that 650 Kelvin's a little bit too high for a temperature. However, right around that area is what the actual critical temperature is, as shown here. So, we've done what the homework has asked, we've done what the question has asked. Thank you very much for watching. I hope you have a wonderful day.